So welcome everyone. I'm Nicolas Bérubé, and I will continue to present work that has been done at the University of Montreal. This work has actually been, everybody can see that okay? I can't really. Okay. So this work has been motivated by the search for low band gap polymers. And low band gap polymers actually have plenty of applications, mostly motivated by a greater photon absorption in solar cells, but can also be used as suitable candidates for organic transistors or organic infrared devices, or just organic materials with higher dielectric constant, which would have higher charge mobility. One way to look at the band gap of a polymer would be to look at its aromatic versus quinoid form, which means the structural form. And the difference here, we have an example, the polythiophene in its normal aromatic form, and the polythiophene in its quinoid form. And the difference between the two of them, for those the most astute of you, is that the aromatic form has actually the simple carbon bonds in between the monomers, while the quinoid form has double carbon bonds in between the monomers. Normally, for most polymers, they tend to be more stable in their aromatic form. But one can force the quinoid form of a few polymers, for example, polythiophene, by fusing an aromatic cycle, for example, fusing a benzene cycle to the thiophene ones, which forces the quinoid form of the polymer, which makes the quinoid isothiophene in this case. Now, the link between aromatic and quinoid form and the band gap has actually been discussed by Jean-Luc Breda more than 25 years ago. So it's actually very old, but this link, to my knowledge, this relationship hasn't been fully extended or fully applied. What he found in his study was that for only polythiophene, he actually forced the structural constraint of the polymers, and he forced the bond length to to span the whole range from aromatic to quinoid, and he calculated the theoretical band gap of polythiophene. And what he observed is that the low band gaps actually stand when the polymers are in between its aromatic and quinoid form, where all the carbon lengths are almost equal. Now, the goal of this research was actually to, well, there are more performance theoretical methods today, so what if one can use these methods and try to generalize this relationship and try to expand it and to apply it to polymer design? So the method that has been used right here is actually an accessible density functional theory calculations, which is a theoretical method to obtain electronic properties such as energy levels and band gap. What we used here was the B3-lib functional, Gaussian zero-line code, and a Gaussian localized basis set, which is very normal stuff in the literature that has been still used by a lot of people. The problem when one wants to generalize this relationship for polymers is how to quantify this factor. Now, Jean-Luc Breda used actually the bond difference, the bond length difference between the perpendicular bonds, the double bonds, and the parallel bonds, the simple ones. So he actually calculated the double ones, the simple ones, calculated the difference, and then said, here's my parameter to calculate if my polymer is aromatic or quinoid. That works very well for polythiophene, but there's a lot of polymers out there, and for example, just for a benzene molecule, then there's a problem. It's that there is no double or simple bonds in the benzene molecules. It's actually delocalized. And there's every bond is delocalized in the cycle, and you cannot identify which ones are the double ones and which ones are the simple ones. So right now, right away, this method doesn't work. And if one wants to use, for example, benzodithiophene, now this gets more complicated in trying to identify the links and which one are parallel, which one are perpendicular, which one are the simple, the double, and how to quantify this. So after a lot of trials and error, and I say a lot, the method that we found that would give a link between this parameter and the band gap, we actually wanted a simple, the most simple, please, dimensionless parameter in order to quantify this structural form. And the idea that we had is to simply take the average of the intermonomer bond over the average of the intramonomer bond. And the logic behind that is that for example, a polymer in its aromatic form, they actually have the intermonomer that are the simple ones, And when you look at the carbon lengths inside the polymer, inside the monomer unit, there would be more double carbon lengths. So on average, the average would be shorter. And for the quinoid, it's actually the opposite. The double bonds would be in between the monomers, while inside the monomer, there would be more single bonds, which would be longer. That means that this factor would be over 1 for aromatic polymer and under 1 for quinoid polymer, which is a start to quantify this structural form in a simple way. We actually chose, this was a somehow arbitrary decision, which would give this simple result in order to try to compare the most radically different families of polymer. We actually chose to look at the average of sp2 hybridized carbon-carbon bonds in the shortest path cycle in the monomers. So here in red is actually an example of the rejected carbon bonds that we did not consider in the average. We didn't consider the bonds with atoms other than carbons because by default, those bonds are not the same length. So if you want to obtain dimensionless parameter, we would have to compare to the bonds in equilibrium and to try to weight by the type of bonds, and we wanted to keep it simple. And anyway, the delocalization of the form is in between the carbon bonds, so the effect is right there. We also tried to ignore the aromatic fused cycles, because if we wanted to compare this, but those atoms would be replaced with nitrogen for thionopyrazine, for example, then we wouldn't consider those bonds because it's nitrogen. But then it's carbon here. So what makes this polymer like, oh, we would consider those carbon bonds but not the other bonds? And we want to compare actually the effect in the main backbone chain. So actually ignore all the bonds that are not in the main chain in the shortest path. And the same reason apply here if we want to replace this atom with nitrogen and compare it to fluorine, carbazole, for example. So this is somehow arbitrary, but this is only to define the parameter. And the parameter is only a secondary parameter in the model that we're going to use. And it's in order to try to explain the relationship and try to guide the design. So here's actually the result. We actually launched this calculation on 87 homopolymers, and we find the same thing that Jean-Luc Breda found 25 years ago, so yay, 25 years late. But the main difference between Breda's study is that in Breda's study, we only had polytyrene in forced geometrical configuration, while here we have 87 radically different polymers from radically different families, all in relaxed geometrical structure, and they actually all tend to follow the same trend, which low band gap lies in between the aromatic and quinoid. Now, it's very great for homopolymers. But what about copolymers? What if we start mixing them up? Well, I launched calculations on another 100 polymers, and they all tend to follow the same quantitative relationship, which is very great. There is actually a zone around the zero band gap, the metallic polymer, that seems to be excluded. And this is an effect that is found in polyacetylene, for example, that forces at least a small dimerization that will tend to eject the polymer either from the aromatic side or the quinoid side. But one can see that we can lower it as low as 0.5 electron volts, around 0.5, 0.7 electron volts. Now the goal here is to try to predict it. We want actually to predict the copolymers where they would fall before launching calculation, at least as a thumb rule. The most common approach that is going to use to try to find this thumb rule is the push-pull approach or the donor acceptor approach. And the logic is that you actually take a unit with a HOMO and LUMO level, another one with another HOMO and LUMO level, and the mix between them will be the lowest LUMO and the highest HOMO. Here's a new band gap, it's lower. You have your new copolymers with low band gap. Yay. Now my approach actually says that no, you actually mix an aromatic one and a quinoid one, and they will mix into this copolymer, which will be in between aromatic and quinoid, which will lower the band gap. Now this model doesn't say anything about the precise place of the HOMO and LUMO level, because this depends on, for example, if you use nitrogen or oxygen or all those other handy add-ons that we pushed aside at the beginning of this talk. Now the prediction models, we actually tried to compare those two, which one works better quantitatively between the quinoid one and the push-pull approach. So we tried to predict the data on 113 copolymers based only on the data of the homopolymers. The quinoid model takes the average of both band gaps and completely ignores the quinoid parameter, dimensionless parameter that I used. It's weighted by the number of carbon-carbon bonds, so that big units would have a bigger effect, and it excludes this forbidden red zone area under 0.5 electron volts. Here's actually the results. In the blue dot is the Quinoid form, the Quinoid model, and the yellow dots is the push-pull model. So on the y-axis, you can see the model band gap that has been calculated in a few, shorter than a second, with just a simple thumb rule. And the x-axis, the horizontal axis, is the beat relay band gap that has been calculated after long DFT calculations on the polymers. The dotted line, the dashed line, is actually the perfect agreement between the two. If all the points were on the dotted line, we wouldn't need DFT anymore. And one can see that the yellow dots tends to be just a really big mesh of cloud that doesn't seem to hold any predictive power. The blue dots tend to hold at least qualitative power, but at least would work as a thumb rule. There is a whole bunch of dots on the bottom of the graphic here, and it's only because all the polymers that my model would predict to be under 1 electron volt, right here, under this line, all the ones that my model said, they would be under 1 electron volt, or at least they have a good chance to be. I launched a calculation on them, and half of them were indeed, after DFT calculations, under 1 electron volt. So this is a nice pre-selection, and at least all of them were under 1.5. So this actually holds on as a thumb rule, or actually as a qualitative rule. So a few examples of the very, very low band gap polymers around 0.7, 0.8 electron volts would be to mix a Quinoid unit, which is an example of 4 Quinoid unit, and to mix them with aromatic units in order to try to go in between them. So here is a few mix. One can take notes if you want, or if you're not quick enough in a pencil, you can see me after my talk. I would gladly draw them for you. A few last words on reorganization, energy, and mobility. Now, when a polymer is in between aromatic and Quinoid form, all the carbon bonds tend to be delocalized, which means to be of equal lengths. And one can ask if this polymer is still stable, and how does it react to light? Do the carbon bonds tend to deform more or less to light, and how does it affect charge mobility? So I actually launched time-dependent density functional theory, TD-DFT calculations, to look at how the polymer would deform upon photoexcitation. And to look at how much energy the polymer would lose in this deformation. And one can see that the lower the band gap, the lower the deformation, and the lower the reorganization energy is. So low band gap polymers actually are more stable, are more solid than high band gap polymers, which means that they deform less upon photoexcitation, and the charge carriers would be more mobile in the polymer. So in conclusion, the low band gaps lies actually in the balance between the Quinoid and aromatic structures that can be obtained by mixing aromatic monomers with Quinoid monomers. This trend actually is a better qualitative prediction than common push-pull model, at least for band gaps, and this still has to be seen how to predict it for the precise HOMO and LUMO energy levels. And the low band gaps actually have potential for better charge mobility and lower reorganization energy upon photoexcitation. So thank you very much. Here are my sponsors, and I'll take your questions now.